Hello, I'm Tyler Cole, and this is my presentation Exploring Pokemon, a relational data analysis using PokeAPI. The motivation for this project is that Pokemon data is rich and interconnected, spanning species traits and form-level battle statistics. The goal of this project is to create a relational SQL database by collecting data from PokeAPI to analyze relationships and trends across Pokemon attributes, and to enable insights into how species characteristics align with form-level stats. For the data collection portion of this project, I collected data from the Pokemon and Pokemon species endpoints from PokeAPI, which had form level stats and species level traits, which are listed here. And I used Pokebase and Pandas to extract this information and add it to the data frames. The data frames I created were DF Pokemon, which had the form level data, and DF species, which had species level data. Some challenges I had were alternate forms of Pokemon, which shared the species IDs but had different form IDs, which caused duplication when merging by ID due to there being multiple forms per species. And to solve this, I created a source form column in the species data frame, which was the same as the name column in the Pokemon data frame and allowed me to merge by name and source form. For data cleaning and integration, I dropped unnecessary columns like the sprite column, which had no information necessary, and I standardized text fields to all lowercase and converted the nested list to JSON format and ensured correct data types across all the columns. And then I merged DF Pokemon and DF species into DF final, again by name equals source form for full integration. For my relational database schema, I created Pokemon DB, which had the form level data, which had the same columns and information as DF Pokemon, and those were ID. The columns were ID, name, height, weight, stats, types, and abilities. And a same thing for species DB, which had the species level data and the same columns as DF species, which were ID, species name, is legendary, is mythical, gender rate, habitat, etc. And the only relationship they had was shared ID, which was the primary key for both of them. The first query I did was stats by weight group, where I used a floor of weight divided by 100 to group by weight, and I created a line plot showing the trend of total stats increasing with weight, which makes sense. The next query was count by egg group, where I aggregated the count of the egg group 1 column from species DB, and I created a bar graph showing which egg groups were the most common. Then I did a speed versus weight scatter plot where I selected the weight and speed for each Pokemon in Pokemon DB, and I graphed a scatter plot which showed that heavier Pokemon were often slower. However, there were some outliers. The next query was a legendary versus non-legendary comparison, where I got the average speed and weight for both Pokemon that fit the legendary category and those that didn't. And then I created a comparative bar chart which showed that legendaries tend to be heavier and faster than non-legendary Pokemon. The last query I did was stats by habitat, where I grouped the Pokemon by habitat, calculated the total stats, and counted how many Pokemon are in each habitat. I created a bubble plot where the size of the bubble is how many Pokemon are in the habitat, and the y-axis is the average total stats for that habitat. In conclusion, I built and normalized a relational Pokemon database using PokeAPI, and I overcame the challenges of alternate forms and inconsistent merges. And then I created integrated visualizations that revealed trends by weight, habitat, and classification. And by creating this database, I enabled structured querying and deeper exploration through SQL.